Very good morning, students. Today lecture we are going to discuss about KVL, KCL, and some of the voltage sources and current sources. Okay, so there's a difference between the voltage source and current source. Okay, so which source we are using, either current source we are using or voltage source we are using. Okay, and some are the basic problematics on KVL and KCL. Okay, so today let's just go only deal with the KVL and KCL. So just go to the laser. Okay, after the session, so I will send this PPT in the form of PDF. Okay, so then go to this PDF and check the if the material is missing. Okay, so let me start. So KVL and KCL. So Kirchhoff voltage law and Kirchhoff current law. So here Kirchhoff voltage law, current law are the both are the same. Okay, so we can say that these are both combined with the Kirchhoff laws. Okay, so in the Kirchhoff laws, there are the first one is the KCL. Okay, Kirchhoff current law and Kirchhoff voltage law. So both are related to in the form of, okay, so which are related to the resistor in the, okay, so KVL KCL are the for the resistor. So in the resistor network which are going to use, okay, that is a KCL and KVL. So problematic to find the current in the circuit. Okay, so voltage level, so how much voltage is flowing through the, okay, so how much current is flowing through the, so these are laws. So here, so based up the name, okay, the Kirchhoff laws is comes from the Gustav Gustav Robert Kirchhoff. Okay, so a German side, German physicist. Okay, so from that one, the laws are known as a Kirchhoff current law and Kirchhoff voltage law. Okay, so here let me go to the circuit. So here is the, so here is the one restored bit. Okay, so this is the bridge. So here is the combinant. So these are called as a one bit. So this bridge is named as the restored bit, and the component label, which is the G, is the galvanometer. Okay, so before going to the Kirchhoff laws, just discuss about the what are the components we have. Okay, so here is the voltage source, so indicating the E, and resistors combined, okay, in the form of a bridge. Okay, and here is the galvanometer is connected. Okay, so here is the, so here this type of circuit is to calculate the value of the unknown resistor. Okay, so here to find out the unknown resistor, so we're having the voltage source is there and current measuring, okay, and the resistor. Okay, so here is the current flowing through this. So to find out this resistor, okay, so we are, so the other are three are the variables. Okay, and so that is the, so it cannot be reduced the zero. Okay, so due to the unknown circuit, okay, so we cannot be reduce that circuit, right? So for this one here, so we don't know about the this Rx value. Okay, so if we don't know about this Rx, so we cannot find the total resistance in the circuit. Okay, so we have to find out this the Rx value. To calculate this, so we have to using the this. Okay, so first is the cannot be reduced. Okay, so series and so we cannot reduce, so we don't know about the what is the Rx value. Okay, that's why we cannot go for the reduce the series and parallel circuit. And one cannot find, okay, we cannot find the total equivalent. Okay, so due to the we don't know unknown resistance, that is Rx. Okay, so here, so which is that is a Kirchhoff current and voltage laws are used to solve this circuit. Okay, so to solve this type of circuit, we are using the Kirchhoff current and voltage laws. So here is the first one, Kirchhoff current law. Okay, so here Kirchhoff current law state that the algebraic sum, okay, the algebraic sum of the currents at the node point. Okay, this is the node point, the current at the node point, the algebraic sum of the current at the node in the network at instant time is 0. Okay, so here the we are saying that the current, okay, at the all the currents we are coming to at this node, the current is 0. Okay, so that is the we can indicate. So all the currents are towards this one. Okay, at this point the current will goes to the 0. That is the Kirchhoff law. Okay. So Kirchhoff law is that the algebraic sum of the current at the node that is equal to in the network at instant time is equal to 0. Okay. So and other we can say that. Okay. So we can so it's the okay. So here you can see here one of the thing you can observe the current. Okay. So we can always like another type also we can say the current at the towards them. Okay. So current inputs current is equal to output current. Okay. So here the Kirchhoff law can say that. Okay. Current law we can say that. So algebraic sum. Okay. The algebraic sum of the current in a network at the point node is equal, network is equal to 0. Okay. Or we can say the current inverts to the circuit is equal to the current at the outside. Okay. So input. So direction we can see. So I1, I4, okay, I3. So the network, okay, here that we can say that I1 plus I4 plus I3 is equal to, so here the outgoing current, that is the I5 plus I2. Okay. The input current is equal to the outgoing current. Okay. So input current is equal to outgoing current. That is the KCL. Okay. So KCL. So here to each node in a circuit, we will assign the letter or number. Okay. So here A, B, C are the nodes and N and C are the principal nodes. Okay. So here the node is the selected as a reference node, and you can see this one. Okay. So here we are selecting. So this is the node points. This is the A, N, B, okay, C. So these are the node point. So here is the reference. So here these are the branch. So this, okay, so total this one, okay, so A, N, C, A, okay, A, N, C, A. So we can call it as a, this is the one loop, okay, and N, B, C, N, okay. So it's a loop 1, here is the another loop, this is the loop 2, okay, N, B, C, N. So this is the another loop 2, okay. So this is one closed circuit, this is the another closed circuit, okay. So this is the one element, okay, resistor element. So this is the voltage source. So here is the voltage source circuit, okay. So R1, R2, R3. So the voltage source, so we can calculate. So we are based upon the input connection, just we are give the circuit, okay, that we are here give. So we can see, so each is node gets sent to the letter, okay. Figure 3, A, B, C and N are the nodes, and N and C are the principal nodes, okay. The principal nodes are those they with the 3 or more are connection, okay. Node C select as a reference node, okay. So V is the voltage source between the A and C, okay, and VB is the voltage between the nodes B and C, okay. V is the voltage across the N and C, okay. All nodes voltage is having the reference nodes. So substitute the VA for VAC, VB for VBC, VN for VNC. So just what you are telling that here the voltage, okay. So for this node, so across this voltage, that is the VNC, okay. So this is the, that is the VA, okay. So VA, VB, okay. So and this is the V, that is the voltage, okay. So across the voltages, that's your referencing. So this is the A, N, B, okay. C are the node. So C is the, here is the reference node we are taking, okay. And this the all are having the branches. So VA, VB are the voltage sources. So assuming, so here we are considering the here assuming one loop. So assuming the loop currents I1, I2 are leaving, okay. So I1, I2 are leaving at node 2 and I3 is entered node is shown here. So we can see. So here that we can say the I1, okay. So I1 is net, okay. So that is the here I1, here I2 and I3. So entering current. So what we are doing, the current is leaving from the node N, okay. The current is leaving from the node N, and I1 towards the A VA and I2 to the second circuit, okay. I3 in the rest. So here according to Kirchhoff law, okay, at the node point, okay, at the node point, all current equal to the 0. Algebraic sum the current is equal to the 0. So that is the direction. So that is the we are giving the at the node point, okay, at the node point we are taking, okay. So that is at the node point N, that is the I1 is going, okay. So I2 is going, and but I3 is coming from like this, okay. You can see. So I1, I2 are leaving, okay, and I3 is flowing. That's we are taking as a I1, I3, okay. So I3 is the place, okay. So I1, I2 is leaving one, that is the leaving, okay. That is equal to 0, or else we can write as the I3, okay. So incoming current is equal to outgoing current, okay. So both are the same. And here, so the Ohm's law, okay. So by using Ohm's law is solve the circuit, okay. Then resistors we obtain for the fall, okay. So using the Ohm's law and solving for the circuit current, okay, through each resistor, okay, we obtain the following circuit. That is I is equal to VR by R, okay. If we take a resistor, okay, so where R is the voltage across the resistor R. So at the time, so let me draw the circuit. Here just we are taking the resistors, right. So this is the node A, is the node C, the node A, okay. So we're having the VB, VA, okay. So resistors, so I1 is equal to the R1, okay. Let me see. So here is R1, R2, okay. So R1, R2, R3, so that we do, okay. See, so here from that one, so just the I1, okay. So we are taking the resistor, the current is leaving, okay. So we are applying the Ohm's law for this one first, okay. Then another, okay, that we are applying, you can see. So here is the R1, R2 is the R3, okay. So positive, negative, positive, negative, okay. Current is I1, is the current is I2, is the current is I3, positive, negative, negative, positive, okay. Just giving the circuit. So from the, okay, I is equal to VR, okay. So resistance of Ohm's law, okay. From the Ohm's law, so just we are writing the current in this one, I is equal, okay. So is equal to VR by R. So from the Ohm's law we can write the I, V is equal to IR, I is equal to V by R, okay. That's we have written. So that is a where is the voltage across the this resistor, voltage across the this resistor. So I1, so voltage, so if the nodes are appearing, that's a voltage, the this is the operate, okay. So VA and VN, that's a VR is nothing but voltage that in between the nodes, that's why VA minus VN by R1, okay. Similarly for R2, okay. So that is the resistors across it, okay. That is the I2. So here VB, right. So VB minus VN by R2, okay. So for I3, that is the current in this. So node, okay, at node point the voltage is the VN by R3. So substituting the values for I1 and I2 and in equation 1, okay. So that we get the I is equal to, okay. So here you can see again So this is the equation 1, that is I3 is equal to I1 plus I2. Okay, so that we are substituting. Okay, substituting the values of I1, I2 in the equation 1. Okay, so I3 is equal to, okay, so this is the I3 is equal to I1 plus I2. Okay, so here is the I1 curve, here is the I2. So from that one we are getting, so here can be solved. So for every volt, okay, this can be solved for voltage and current by using the node voltage analysis. Okay, so it can say the node voltage analysis. This is one. So here is the one the problem. So here in this problem, so we are assuming that, okay, so R1, R2 and is the R3. So directions, okay, so always remember that the node directions we are taking. Okay, so in this example you can see, so if the voltage, okay, so VA, VB, okay, remember the direction, so positive, negative. Okay, so is positive to positive, then here it comes if this positive, negative. Okay, this is the loop one. Next here if it comes, so that's the direction, so positive pass. Okay, this time. Next here direct assumption. Okay, so based on assumptions we can assume the directions. Here the assumptions you can see VA, VB. Okay, so VA, here is a VA, VB. The voltage that is the 60 volts and here is the voltage is the 20 volts. So resistor, that R1 resistor having the 8 ohms, R3 having the 4 ohms, R2 having the 6 ohm. Okay, so here if you solve this problem, okay, by using that. So in the previous we are taking that is the I3. Okay, so at node 2, so here is the at node 2, the current is the I2. So we have to write that is the I2 is equal to I1, okay, plus I3. So from the KCL, so we can write the I2 is equal, that is the here I2 we are taking. So is the current that I2 is equal to I1 and I3. So first we'll assume the direction of the current flow, then mark the node, okay, and plot of the each resistor, that is the positive, negative. So from that with Kirchhoff current law at node N, so we're writing as a I2 is equal to I1 plus I3. Okay, so from that one we are taking, so Vn by R2 node at the voltage. Okay, so Vn by R2 resist to R2 and current I1 I3, so Va minus Vn. Okay, so that's the voltage across the resistor R1. Next voltage across the resistor R3. Okay, so we are substituting this one, so then we'll get the, okay, so here we get the fraction column. Okay, so from that one 4Vn, so from this, so for solving fractions here, by solving this fraction we get the 4Vn is equal to 3 into 16. Okay, here we get 6 into 20 minus here. So by solving we are getting the node at the voltage, that is the 23.077. Okay, so third, find all voltage drops and current. Okay, so if we are getting the null voltage, that is the Vn value. Okay, from this value we can find the voltage. Okay, so voltage at each volt. Okay, so voltage across each resistor we can find. Okay, this is the one method. So here the negative value of the V3, okay, the negative value V3 shows that the actual current direction through the R3 is the opposite to the assumed current direction. So what we are getting, so we are here in the circuit, you can see the R3 directions we are current. So is the positive, negative, right? We are direct there. So if we get the negative directions, okay, that's why we are getting the value is the what you are assumed, whatever the way I have assumption that. Okay, so V3 is assumption, that is the in the negative. So that's why getting the negative. If we get the positive, so we'll getting the in the positive way. Okay, that is a different. So whatever you get, assumption, so either positive or negative. Okay, so we'll get the based upon the assumptions one. Okay, so if you take in positive direction or negative, okay, so nothing, just you have to assumption that positive and negative assumption. Okay, so again I will explain. So here is the one circuit we'll have. So from the circuit, this is the R1, R3, R2. So just we have assumed that here is the positive, negative. Okay. So here also we can assume. Okay. So here that is the negative, is the positive also we can. But here they mention. So so just we have assumed the positive, negative. Okay. So add the nodes A, N, B, C. So also we can assume that A, B, C, okay, D, E also we can observe. So we can say this is the loop 1, here is the, we can say this is the loop 2. Okay, loop 1, loop 2. Okay, so that is the node 1. So from that one, okay, node analysis. So this is the node N. So from this one, we are taking that the current directions we are getting. That's the I1, I3, I2. So suppose if we get, okay, so from this one, the current is, that is the I2. Reference we are taking the C. So from that one, I2 is equal to, okay, so I1 plus I3. Okay, that way. So we are get assumption current directions we are assuming. Okay, so here is a positive, the positive resistors. Okay, so negative direction. Okay, so it will. So resistors. So voltage across the resistor R1, that is a V1. Voltage across the resistor R3, that is a V3. Okay, voltage across R2, that is a V2. So from that, so we are getting the I2. Okay, the resistor V2. Okay, so we are getting that is a V2. Okay, so we are taking the V2 minus by. Okay, so V is, so from the V equal to IR from the Ohm's law, we are writing the I is equal to V by R. Okay, that's we are assuming. So each resistor. So that is a I1, I3. Okay, we are writing. So here one, the node resistance. So Vn by R2. Okay, each resistance we are taking. So you can get the one dot here. So here we get the node N. So we have to take the node voltage, that is a Vn. So then this the V2 is the voltage across the R2. Okay, this is the nodal voltage. Okay, so Vn. So this is the Vn. Okay, V2 is the resistor. Okay, voltage across the resistor only. So this is the voltage, that is a Vn, Va, Vb. Okay, Vn by R2. Okay, this is the way. Okay, we have to get it. So this is the KCL and KVL. So next we are having the star and delta circuits. So here, so what is the need of the, okay, so what will get, so what is the need and purpose of the star connection, delta connection? Okay, so here we'll get, so while applying the KCL and KVL, the number of simultaneous questions will be solved. Okay, so increase when network is complicated. So while applying the KCL and KVL, okay, so if the number of simultaneous equations will be solved, okay, if the increase, so at the time, so if the 3 or 4 resistors, then okay, it will be easy. But while coming to the, if the number of circuits if increases, okay, that is a very complicated. So at that time, okay, so complicated net can be simplified by applying the star and delta control. Okay, by applying the, that is a star and delta formation. So what is mean branch? Okay, so here we have to know what is, so what is mean by branch? So element is connected between the two nodes or junction. Okay, so if the element, here we are connecting the resistor and here this, so this is the node, this is the one branch. Okay, so this is called the branch. Okay, this is the junction or node point. So element connected between the two nodes or junction. That's called as the branch. Okay, a branch will having the two ends. A branch will having the two ends. So you can see this is the first end, this is the second end. So the two ends may be designed to starting and finishing. So first starting and finishing end like that. Then the starting ends S1, S2, S3. Okay, we are getting, so we are taking the three branches, that is the starting ends we are having the S1, S2, S3 and finishings we are having the F1, F2, F3. Okay, so of the three branches can be connected into two fashions. So that is the we are connected within the fashions, that is the that's the star connection or T connection. So that if the three resistors if connected, okay, the two type. So that is the star connection or T connection. So that is the next we having the delta or mesh connection, delta connection or mesh connection. We can say that is a pi connection. So this is the star connection means, so T. So getting star means, so you can take like this. Okay, or you can connect in this way also. The star connection or T connection, Y connection, whatever it may be. Okay, so but coming to delta. Okay, so in this delta, so here is also the phi connection is with this one like this. Okay, so phi connection, star connection. Okay, in the star connection all the similar nodes, that is either starting or finishing and are connected together. Okay, so this is nothing but the in the form. Okay, other terminals like this. Okay, the Y connection or star connection we can say. So all the ends, okay, all the first ends are finishing ends connected at one point. So you can see here the first end we are connecting the this one. Okay, so all the second ends are connected at this point. So like this. So first end, finishing end, starting end. Okay, so you can represent it. Next, in the delta connection, all the dissimilar ends connected together. So here is the this is the positive, negative, this positive, negative, positive, negative. Okay, so or else finishing end, starting end, starting end, finishing end. Okay, starting end, finishing end. Okay, so in this way. So this is the in the delta connection all the dissimilar ends are connected together. Okay, the finishing and the first coil is connected to the starting and the second coil. So is the if so just we are assuming, so starting and finishing ends. So here if we are observing this the starting end of the S1. Okay, so A is the S1, here is the finishing end and this is the starting end. Okay, so here is the 2. Here this will having the finishing and we are having the connected finishing like this. So if we connect it like this coil, that is the delta connection. So we can say in the form of the pi connection also. Okay, so here how can we transfer? So transformation of star delta to star. Okay, so here the this is the delta. So we have to convert that into the star. Okay, so we can convert this one. So is the one form. So these two arrangement will be electrically equivalent. Both are electrically equivalent. So if the resistors as measured between any pair of the terminals is same in both arrangement. So here if the resistors okay in the measure between any pair, so any pair of the terminals is same in the both arrangement. So transformation of the delta to star. So this is the first we have to consider the delta connection. Okay. So first we are getting to that is the delta to star. Okay, so we are assuming the resistors. Okay, terminals A B C. Okay, so if the resistors RAB, okay, resistors across BC, that's RBC, resistance across this AC, that's a RCA. Okay, so between the terminals A and B, okay, so the terminals will having the two parallel paths. So this is the one parallel, this is the another parallel. So first we are having the RAB, and second path is the RBC and RCA. Okay, so total resistance between the A and B. So first path, so between the, so considering that, and between the A and B, so we're having the two parallel paths, that is RAB. Okay, next we're having the RBC and RCA, so we're having the two parallel paths. So from that one, here total resistance between the terminals A and B. Okay, so we can write as in this form. So if both, okay, so RBC RC are connected in series. Okay, so then that connected to the parallel. Okay, so from that one, writing the this equation. So product by sum. If the two resistors connect in parallel, so we can write the parallel by sum. Sorry, product by sum, that we are writing. Okay, so from that one, this is the RA, RB, RC. So in the star connection, okay, so the one. So in the star connections, we are assuming that AB, okay, so star connection resistance between the same terminals that we are connecting the RA, RB, RC. Okay, so from that one, resistance, terminal resistance have the to be same. Okay, so RA plus RB. Okay, so just we are assuming the RA plus RB. Okay, so that we are taking. So at the terminal resistance, okay, resistance have to be same. So RA plus RB. Okay, RA plus RB. That is the total resistance. Okay, so similarly for the if we connecting. Okay, that is the what we are doing here. Okay, so it's the A, B, C. So from that one, we are getting like this. Okay, so from this one, this is the RAB. Okay, so this is the RBC. Here is the RCA. So this is the, so from, so in between, so if they wanted to find the RA, okay, so here we are taking, so here is the RA, RB, RC. Okay, RA, so RAB. Okay, so from that one we are writing. Okay, so we are converting this R into like this. So from RA plus RB, so RA plus RB, we are getting the equation like this. Okay, so similarly for RB plus RC, so just we are assuming that here we are having the resistors, right? So this is the RAB, RBC, RCA. Okay, so note A, B, C. Okay, just we are. So from this one we are writing. Okay, this is the RA, RB, RC. So if I wanted to find this RA, okay, so from this term RA, okay, RA and B, so both are connected. Okay, so from RA, RB is equal to, okay, RA, RAB, okay, RBC, okay, RA plus RBC, that is parallel to the RAB. Okay, so that's we are taking RAB, that's we are taking. Okay, so for this we'll get the equations. So from the equations, Okay, so A and B, terminals A and B, we get this equation. Okay, similarly for B and C terminals, we'll getting the RB plus RC is equal to that we are getting. Okay, for next for the terminals C and A, okay, this is for the equation. So just we are adding. Okay, so what we are getting, so RA RB are then we are get. Okay, so both are in series. Okay, this is the at the parallel, so that's your consumption. Okay, so first, okay, so first while using the RA and RB, okay, while getting the while taking the A and B terminals. Okay, first we are taking A and B terminals, so that is the RA plus RB. Okay, so this is the RC. Okay, RCA. Okay, so next, okay, so we'll having the these ends into the this. Okay, so while taking the this one, so we have the assumption. Okay, so from that one, so substitute the equation 2 in the equation from equation and getting the result. Okay, so from this one, so this is the equation 1, equation 2, equation 3. So here subtracting, okay, equation 2 from the equation 1, so which are equation 2 from the equation 1. Okay, if you subtract, we'll get, okay, subtracting equation 2 from the equation 1 and that we are getting, okay, adding the result to the equation 2. Okay, so what we are getting, so we are taking the equation 2, okay, subtracting the equation 1. Okay, so that we are adding to the equation 3. Okay, that result we are adding with the this. Okay, then we are getting the RC is equal to RA into RBC. Okay, by RA plus RBC into RC. Okay, so similarly, so one thing we have to remember here in the delta 2 star. Okay, so delta 2 star confirmation, so this is the A B B C C A. Okay, those the R A R B R C. Okay, so if wanted to find, okay, so formula, so R from this one, okay, here A B R A is equal to R C. Okay, adjacent. Okay, adjacent of the, so here is the resistor RA. Okay, so this is the RAB. Here we are having the RCA. Okay, adjacent. So product of the adjacent by total resistor. Okay, RA is equal to product of the adjacent resistor. Okay, by total resistor. Then that will get the each one. Similarly, so if the for BC, okay, so this is if they take the RB, so at that time we'll having the RA and RBC, okay, RAB, RAB, okay, then total resistance. That is a simple. Okay, so if wanted to find, so just I'm giving the, so here one resistor we have, right? So in the delta, so if wanted to find this, okay, we are lighting in this way. So if wanted to find this resistor, okay, from delta to star, so we have to take these sides. Okay, so product of these sides resisted by total resistors. Okay, so products of the adjacent resistors by total resistance, then we get the each resistor. Okay, that is about the delta to star. Then we having the transformation, that is the star to delta. So in the star to delta we have, so star connection, then we are converting that is into the delta. So conversion of the star to delta can be obtained by multiplying the equation 1 and equation 2. Equation 2 to the equation 3. Okay, so which are taken in this one. Okay, so equation 1 2 3, okay, that we are taken, right? So just we have to multiply, so we have to multiply the equation 1 to 2, okay, and multiply the equation 2 to 3 and 3 to 1. Okay, RA, okay, so RA, RB, okay, RB, RC, RC, RA, okay, just. So what we are melting, so we have to find out, okay, if you are taken, okay, so at this time, so we have to, this we have to loop, okay, so we have to take, okay, so multiply it, AB, okay, next for B at the point we have to find, that is the equation 2 to 3, then we have to take this one, just multiplication, okay, if wanted to from delta to star, okay, so if take this, wanted to find this resistance value, so we have to product of the adjacent resistance and total resistance by total sum resistance. So adding the term together will get the simplified RAB, okay, RA plus RB plus RAB by RC, okay, that we are getting. RAB is equal to, RAB is equal to RA plus RB, okay, RA plus RB plus RAB by RC, okay. Similarly for here, RBC is equal to RB plus RC plus RBC by RA, okay. So which are taken, so if wanted to find RB, RAB, okay, total sum by, this is the product by sum, okay. So this is the for the formulas for star to delta, okay. So here star connection, okay, so T connection, Y connection, so called as different name according to step. So both diagram, so both will be same, either star connection or T connection, okay, so both are equivalently same. So either phi or del, okay, so both connections will be having the same, okay. So one thing we have to, so if the question if they come, so we have to observe this is the delta, okay. So if the line, so we have to specify that is the pi connection, so both are the equal. So the star to delta comes different ways to connect in the passive network, okay. When analyzing the such network, so useful to, so while the doing the problem, the length problem, so it will be easy for delta to star, star to delta, okay. So both are we are needing. So delta circuit can be converted into the equivalent resistance of, okay, star connection, okay, by applying the Kirchhoff laws. So this is the formulas, delta to star, okay, delta to star, okay. So star to delta, so this is the formula, okay. So we can written like in this, okay, star to delta formulas. So just we are absent, okay, in between the sub products, okay. So if one rest, then product by total resistance similarly. So this is all about the star to delta conversion, right? So in the next session, so we'll go for the ideal sources, voltage source, current source, okay. So this is about the today class. Thank you.